to predict if a antibody will cross-react to orthologs in another species. So that I guess that one is for me. So we face this a lot. Right? Customer would come to us and say, hey, your antibody that react with human, can it work with dog, or can it work with lizard, or what's the weirdest one will work with some kind of algae, and then without testing it in the actual specimen, of course, we can't guarantee it, but usually the guideline we follow is the percentage of homology of the sequence that the antibody targets and how similar that is to the antigen ortholog in the ortholog protein in the other species. Now, one thing that's kind of special that we found, and I'll go to that special thing later, sorry. Usually our guideline is if the overall sequence is about like 90% similar or more, there's a very high chance of it cross-react. Anything lower than 80, we're kind of advise against it, with the exception that if the sequence is different, but the differences are immunogenicity equivalent swaps. So basically, if you have an I and a V, if they're both kind of just hydrophobic, the short side chains sticking out, one is a little shorter, one is a little longer. If you have those kind of swaps, and you have a lot of those, that's usually a sign of evolutionary conservative pressure at work. Like you can swap a similar thing in there, but you cannot kind of deviate too much from it. Like if you have a lot of those, which is kind of reasonably common, if you have a immunogenicity wise equivalent swaps, you can consider them the same thing. So if you have like 90% or more similar, big chances are your antibodies are gonna cross-react to it. If less, then not advise against. So what about that 80 to 90% in between? That's one interesting factor that we have noticed when I was doing a zebrafish to human ortholog analysis, is that there's actually very small amount of protein that falls in that gap in between. You're either very similar between two species, or you're not very similar between two species. So after seeing that pattern, my theory is, if there's no evolutionary pressure, you're gonna have a runaway kind of mutation between something so different as a human and zebrafish, and it's gonna be very different. But for some proteins, there is evolutionary pressure, and you just cannot deviate from the blueprint, and therefore it stays similar. And therefore, the protein that stay a little bit similar but a little bit different is actually very unlikely to happen. So you're either 95% and above, or like 70% or less between human and zebrafish. I think a similar pattern probably holds for other species as well. That's just my kind of interesting fact I want to add in. So I hope that addresses the question 4. If there's anything I want to add about this, is it's more important what the local similarity of a epitope is. So the whole sequence can be like 70% different, but if you have a local region that is the same, right? If you have one epitope about 20 amino acids long, that's about the same. Chances are your antibody can still cross-react because it's more important for how a short region of antibody peptide can react with the antibody, because the CDR of the antibody, complementary determinant region of the antibody, can only recognize anywhere between I would say 10 to 25 amino acids at best. So if you have a local region that's the same, big chances you're cross-react. All right. Sorry, that's a very longer than I wanted to put it.
Question for you, CJ, if that's okay.
Yeah, of course.
Do you use NCBI's tools to do the alignment to find out what the similarity is and what the homology is, percent homology? Is that, or do you guys have a custom in-house tool that you prefer to use? Can you just briefly?
Absolutely, yeah. Great question. So we do have an in-house tool. And sorry for cutting off. We do have an in-house tool for that. So basically, what we did was we took a sliding window of 7 amino acids across the entire genome of multiple species, and we did a reverse hash table. I don't remember data science wise that's what's called. Basically, we recorded where a particular 7 amino acids long sequence appears in like every gene, right? We did a table like that, and then we use that to create a kind of pre-blast of all the proteins against all the proteins. We use that for homology determination. It's much faster than blast. The main benefit of that though is we can adjust how we consider what we consider similar, right? What we consider similar. So we can have in that way we can easily identify multiple amino acid sequences as similar or equivalent, depending on the application that we're talking about. And then that comes into that becomes very useful when considering the matrix effect that you wanted to talk about, which is just how much abundance a protein is, how abundant a protein is in a matrix. So if there's a huge abundance of a protein like albumin, or if the protein is known to be very sticky, like a Hishack protein family, right? We can adjust the sensitivity of our indication of similar peptides. So basically, if we can adjust sensitivity if the two peptides are just a little similar to a peptide known in the albumin family or in the Hishack protein family, then we can choose to determine that they are the same, right? So that way we can customize the sensitivity of how we decide similarity, and that's just not something you can do with a generic blast algorithm.
Definitely not.
Yeah. So in that way, we can pick out specifically pick out the troublemaking proteins like albumin and all that sticky proteins, and just like basically don't choose to not touch it with an foot pole, right? If you're just a little bit like that, like we will avoid those sequences. That's one thing we're able to do with that kind of approach, and it really helped. Actually, after we implemented that, we first realized that the need of doing that once we noticed that most of the non-specific bands in our internal Western blotting are contributed, like more than 50 of them are contributed by 3 molecular weights. And we look it up, and it's like HSP70, HSP90, and albumin. It's like those troublemakers are contributing more than 50% of all the non-specific reactions out of the tens of thousands of blots that we did, right? Like, so we decided to don't touch it with a FFO kind of approach. And after we implemented that, our background noise rate actually improved by almost 25% after we implemented that strategy. Really helpful. Thanks. Sorry, that's another long answer to your question here. So.